set. We know that set is a collection of well-defined objects. A metric space is a set in which we can talk of the distance between any two of its elements, because in set we don't have a concept of a distance, but in metric space we can talk of a distance between two of its elements. Now the definition of metric space: suppose X is a non-empty set. A function D from the cross product of X and X to the set of real numbers is said to be a metric on non-empty set X if D satisfies the following properties. First one is that distance of X from Y is greater than or equal to 0 for all xy belonging to X, and distance of X from Y is 0 if and only if X is equal to Y. Second, distance of X from Y is equal to distance of Y from X for all xy belonging to X. We call this a symmetry. And distance of X from Z is less than or equal to distance of X from Y plus distance of Y from Z for all x, y, z belonging to X. And we call this property to be triangle inequality. If all the three conditions are satisfied, then D is a metric on X, and we call the pair XT to be a metric space. For example, if we consider the set of real numbers R and we define a metric like distance of X from Y is equal to modulus of X minus Y, then this is a metric, and we call this metric as a absolute value metric. Clearly it satisfies the first two conditions. First condition is distance of X from Y is greater than or equal to 0. Clearly modulus of X minus Y is greater than or equal to 0. Second property is that distance of X from Y is equal to distance of Y from X. Now we know that modulus of X minus Y is equal to modulus of Y from X, Y minus X. So it is easy to see that D satisfies the first two conditions of the metric. Now we will check the last condition, which is triangle inequality. We know that the distance of X from Z is modulus of X minus Z. If we add and subtract Y, so this is X minus Y plus Y minus Z. We have subtracted Y, we have added Y. So it hardly makes a difference. So by the triangle inequality of absolute value, we know that this is less than modulus of X minus Y plus modulus of Y minus Z. And this is nothing but distance of X from Y, and this is nothing but distance of Y from Z. So in the diagram also you can see we call it triangle inequality because sum of two sides of a triangle is always greater than the third side of a triangle. Means distance of X from Y plus distance of Y from Z is greater than distance of X from Z. As one more example, we define the metric as D1, and D1 means distance with respect to this metric from X to Y, like dxy equal to 1 plus dxy. It is also a metric. If we define D1 like this, then this is also a metric. To check whether it is a metric or not, we will check all the three conditions. First one is that distance between 2 points should be greater than or equal to 0. So for this we know that because dxy is a metric, so distance of X from Y is greater than or equal to 0. It means 1 plus dxy is also greater than or equal to 0. It means this d1 xy is greater than or equal to 0. Also d1 xy is equal to 0 if and only if dxy upon 1 plus dxy is equal to 0. If we cross multiply it, we will get 0. So it means distance of X from Y is 0 if and only if X equal to Y, because D is a metric. Clearly distance of x from y is equal to distance of y from x. So we can replace x by y here. We can write dyx and dyx here. So clearly d1xy is equal to t1yx. Now for the triangle inequality, d1xy plus d1yz is equal to dxy upon 1 plus dxy, and dyz is dyz upon 1 plus dyz. Clearly this is greater than equal to dxy plus dyz. This is the LCM, 1 plus dxy plus dyz. And we can write it as 1 upon 1 plus 1 upon dxy plus dyz. And this is greater than equal to 1 upon 1 plus dxz. We have applied triangle inequality. So this is equal to dxz. If you simplify, dxz upon 1 plus dxz. And this is nothing but d1xz by this definition. So we have proved that d1xy plus d1yz is greater than equal to d1xz. So d1 is a metric, and this is important because it is closely related to a metric D. One more example. Suppose x is a non-empty set. We define dxy equal to 0 if x equal to y, and distance of x from y equal to 1 if x is not equal to y. And we call this metric to be a discrete metric. This is a discrete metric, and it is easy to see that it satisfies all the properties of discrete metric. One more example. Suppose we consider n-dimensional real space. Then if we define d1xy equal to sigma k equal to 1 to n modulus of xk minus yk, and d infinity xy equal to maximum of modulus of xk minus yk, where k lies between 1 and n, then these are metrics on n-dimensional real space, and we call this metric d1 as taxi cab metric in USA. This is known as taxi cab metric. If we draw the graph of this metric, suppose this is a point x1 y1 and this is a point x2 y2. So this is, if we calculate the distance of distance between P and Q, the distance between P and Q with respect to metric d1 is x2 minus x1 plus y2 minus y1, because the metric is sigma k equal to 1 to n modulus of xk minus yk, and distance of A from B is x distance between x4 minus x3 plus y4 minus y3. We have applied this because d1 xy is equal to sigma k equal to 1 xk minus yk modulus, means x1 minus modulus of x1 minus y1 plus modulus of x2 minus y2 plus modulus of x3 minus y3, and so on. Now with respect to metric, this metric d infinity, the distance of P from Q is y2 minus y1, because here the metric is maximum of xk minus yk, where k lies between 1 and n. And in this metric, with the distance of A from B is x4 minus x3, because we have to consider maximum of xk minus yk. Here it is clear that this distance is greater than this distance. Here it is clear that distance of this from this is greater than distance of this from this. So in this case, distance between P and Q comes out to be y2 minus y1, and in this case distance from A from B comes out to be x4 minus x3. This is the graphical representation of metric d1, and this is the graphical representation of metric d infinity. Means to calculate the distance with respect to d1 metric, and to calculate the distance between 2 points in 2-dimensional space with respect to d infinity metric. These cases are for 2-dimensional space, and here we have defined the metric for n-dimensional space. Now what is open ball and open set? Suppose X3 is a metric space and X belongs to X and R is greater than 0. Then the subset BD XR means centered at X and radius R, means ball with respect to metric D centered at X and radius R is defined as the set of all the points Y belonging to X such that distance of X from Y is less than R. And closed ball BD from X to R, here we have considered, I have written close brackets, is Y belonging to R such that distance of X from Y is less than or equal to R. This is the open ball, this is the closed ball. This ball is also centered at X and radius R. This ball is also centered at X and radius R. But with open ball we have less than equal to R. In closed ball we have less than or equal to R. And these balls are defined with respect to metric D. So to calculate the distance, we should always take care of the metric which is under consideration or which we are using. We have used these notations to emphasize that metric under consideration is D. Otherwise, we can denote it simply by BXR, and this can be also denoted by with close bracket BXR. Suppose R is the set of real numbers equipped with standard metric. Then we claim that the open ball with center X and radius R is nothing but the open interval X minus R to X plus R. Because if Y belongs to BXR, if and only if distance of X from Y is less than R. Distance of X from Y is less than R means with respect to standard metric, modulus of X minus Y is less than R. And this is possible only if minus R is less than X minus Y is less than minus R is less than X minus Y is less than R. And if we shift X, then it is X minus R is less than X plus R. Y belongs to this open interval. If we consider two-dimensional space equipped with the Euclidean metric D equal to D2, then the open ball centered at 0 and radius R comes out to be set of ordered pairs xy belonging to R square such that x square plus y square is less than R square. Because P equal to x minus ordered pair xy belongs to B0R if and only if distance of P from 0 is less than R. P means ordered pair xy. So distance of P from 0 square is less than equal to R square. So in two-dimensional space, here it is xy, it is 0 0. So distance of xy from 0 0 with respect to Euclidean metric is nothing but x minus 0 whole square plus y minus 0 whole square, and it is already square, so under root will go. So x minus 0 whole square plus y minus 0 whole square is less than R square. We have applied distance, simple distance formula here. So it is x square plus y square less than R square. So draw the figure of open unit ball centered at 0 and radius 1 in the following metric spaces. Here we will notice that the shape of unit ball, in fact open unit ball will change with respect to metric. In the first case we have considered the standard Euclidean norm. With respect to standard Euclidean norm, this ball which is centered at 0 and radius 1 comes out to be the shape of sphere. We know how to calculate the ball. We have explained in last example also. So this ball will come out to be the shape of this. This is the shape of ball with respect to standard Euclidean metric. And this is the shape of ball with respect to d2. And this is the shape of ball with respect to d infinity. We have defined these metric in the previous examples, and we know how to calculate these walls. And if we draw the figure of these walls, these will comes out to be like this. This is a ball with respect to d1, this is a ball with respect to d2, and this is a ball with respect to d3. Suppose we consider the non-linear space X, which is nothing but set of all continuous real valued functions C01 defined on C01 and with respect to norm 1, where norm of f1 is defined like this. This is the integration of 0 to 1 of ft with respect to t. This is the norm f1 defines a norm on the set of continuous real valued function on 0, 1. Thus, if f belongs to 0, 1, if and only if area under the graph of modulus of f is less than 1. For example, f in figure 1 point lies in ball centered at 0 and radius 1, where g in this figure does not lie in the ball. This is the ball, f is in ball 0, 1, and here g is not in ball 0, 1. Suppose xt is a metric space and x belongs to x and r is greater than 0. Then open ball centered at x and radius r is open. Let's see. Suppose y belongs to bxr. Now we need to find s greater than 0 such that a ball centered at y and radius s is subset of ball centered at x and radius r. The figure suggests us what s could be. This is the ball centered at x and radius r, and this is the ball centered at z, and radius is r minus dxz. This complete distance is r, and this is dx, distance of x from z, and here this distance is we have denoted by dy. This is nothing but total distance is r minus distance of x from y. So suppose such as exists. If z belongs to bys, suppose z belongs to bys, we want to show that distance of z from x is less than r. Now distance of z from x is less than or equal to distance of z from y plus distance of y from x. This is by triangle inequality, but distance of z from y is less than s because z belongs to bys, and distance of y from x can be written as distance of x from y. So s plus distance of x from y is less than r. This prompts us to consider that s lies between 0 and r minus dxy. We can shift this to this side. So s lies between 0 means it is always positive, but it is less than r minus dxy, because if we shift this to this side, s will be less than r minus dxy. Let s be like this, which lies between 0 and r minus dxy. If z belongs to bys, then we have distance of z from x less than distance of z from y plus distance of y plus y from x, and this is less than s plus dxy like this, and this is less than r because we have selected s like this. It means this ball centered at y and radius s is a subset of ball centered at x and radius r. Since y is an arbitrary element, we can select any other element also like this of Bxr. We have proved that Bxr is an open set. Thank you.